The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So last week was the intro class and then the human power lab. Today I just told you what we're doing. On Friday we'll have the energy storage lab, and then next week into lighting. So and in 2 weeks is quiz 1, so just so you have it in your minds. So the muddy cards. I'm going to do this one at the end. So one question was, there were some questions on the estimation. So one was, what if I have no reference point for estimation? For example, I have no idea what a D cell is, basically. So then you're kind of stuck, right? Because it's really hard if I ask you to estimate, the power in a glob, and you're like, what's a glob, Amy? And I'm not telling you because it's an estimation, you're stuck. And so if I literally say glob and you're like, I have no idea what a glob is, then you're kind of done and you have to reference some sort of manual. But if you know like D cell is a battery, right, then the best practice is to say, okay, am I familiar with any battery, say a AA or a car battery or a 9-volt or something, and say, and just write an explicit assumption in your estimation. I'm assuming a D cell is a 9-volt or D cell is a car battery, or whatever assumption you make that brings you to something you're familiar with. And that way, when you do the estimation, and if you do it clearly, then when you have time to check that assumption, you can then very quickly revise your estimate based on real world data. And that way, if it's something you're turning into me or something you're using in the real world, you still get to do something, and maybe you'll be off by, have less confidence in that answer at the end. So maybe you're going to be off by a couple of orders of magnitude rather than one, but at least you've done something rather than just sat there looking bored. But if I say glob and you literally are like, I have no idea what you're talking about, then yeah, that's a tricky situation. But hopefully that doesn't come up too often. Yeah, Kurt.
So for the purpose of the problem set, do you want us to kind of pull a number out of thin air for something like how much energy a solar thermal system can produce?
So that wasn't an explicit estimation.
Okay.
So that would be a case where you should be Googling and documenting where you get your numbers, but absolutely looking stuff up. It'll generally, I will say estimate if I mean estimate. But if you're unclear, always ask. I'm not 100% responding to email quickly, but I try to, and if you don't hear from me in like 24 hours, just send another email and be like, seriously, give me the answer. I get a lot of emails per day, as I'm sure we all do, and sometimes it hurts. If you put like an explicit DLab energy in the subject line, that will probably improve my ability to respond quickly, because I won't necessarily recognize your email, but I will see that subject. So yeah, but my intention is to respond quickly. But I got people like emailing me at 1 a.m, needing a response by the next morning, and that is hard for me if I've already gone to bed. Sometimes I haven't, but if I have, I usually don't get to email until midday. So that's just a warning that unfortunately or fortunately I don't keep 2 a.m. hours anymore, usually. I try not to. Another one was a situation where we could actually use estimation in the real world, and I hope that will become clear as the weeks go on. But for example, your community partner may well say, let's put a wind turbine here. Could we do wind power here? And literally that will be the question. And your choice is to say, I have no idea, or yes, or no, or give me 10 minutes and let me do an estimation, and then you can give a much more useful answer than any of those. And so you could very quickly say, well, talk to me about wind speed, and we'll talk about how to estimate wind power later on in the semester. But so, how much are the branches moving? Are you falling down because of the wind? Or, is it just a little breeze occasionally? And get an estimate of the wind speed, and then you can run through a calculation that says yes or no, you could power a light bulb or whatever you want? And those questions come up all the time. Or I really want to do solar power. How much is it going to cost me? And being able to give someone a ballpark by running through the numbers really quickly is great. Or when you're in a job interview and someone asks you these sorts of questions, probably not necessarily about developing country stuff, but just a random question, having that skill will serve you in a job interview, when you're in a consulting job and a customer asks you a question when you're in developing countries. It's going to be useful, I swear. And it's pretty powerful to be able to answer, and instead of just being like, I don't know, I wish I did. So I screwed up and mentioned that the LED was in amp hours, and I sent you guys all an email apologizing for that. So amp hours would be how long a battery can last, and there was a confusion about that. So for example, if a battery has a 2 amp hour rating, for example, which is kind of low, and you know the voltage of your battery, and you know, or the voltage that you're using, and you know the current that you're drawing, then you can use the current to figure out, so let's say it's 2 milliamps is your current, then you can multiply or divide the 2 amp hours divided by 2 milliamps equals 1. I fail at math on the board. Am I blocking the camera? Sorry. So we have 1,000 hours that this is going to last. And again, you have efficiency and issues with batteries that we'll talk about a little bit today. So that's not an exact number that you can rely on, that my battery is going to last exactly 1,000 hours, but it gives you, again, an order of magnitude estimate. Yeah. So does anyone have a question about amp hours versus amps? Batteries? And some of these money card questions, please keep putting questions you have on the money cards, but if you're confused about something, also feel free to contact me or Amit and set up a time to meet, or come after class or before class to talk, because we're happy to help, and we don't have explicit office hours, but we are around a lot and happy to help. So someone wrote, I just want more insight into power, energy, time, and work relationships, and that's a hard question to answer generically, but I'm happy to sit down with you and give you more insight. And then some other quick ones. Background of instructor. I completely forgot to tell you anything about myself other than I have a kid, which is probably the least useful thing for you. So I apologize for that. So I'm a PhD in mechanical engineering. I hope to God I'm in my last year. I've been here a while. I did my undergrad at MIT a long time ago, also in mechanical engineering. And when I finished, I spent 3 years in the automotive industry working for Texas Instruments, which no longer has an automotive sensors and controls division, but did at the time. They sold it off, and now it's called Sensata. And so I worked first as a manufacturing engineer, and then as a design engineer, building pressure switch manifolds, which go into vehicles to ensure that the car transmission is in the right gear, so that if you think you're in drive, the car also agrees that you're in drive and not in reverse, for example, which is pretty safety critical. And then switched over to becoming a design engineer, and primarily worked on capacitive automotive capacitive sensors, which are often used for anti-roll issues, to make sure the car stays flat and parallel to the ground and doesn't flip over. So I have design and manufacturing and industry experience, which was really good. I learned a ton, but I decided that it wasn't as fulfilling or my passion to be working in automotive industry. I really wanted to be working on things that were directly having humanitarian benefit. And while both of those car sensors help a lot to not get you dead on the road in a car, and that's pretty important, it wasn't a good fit for me. So then I quit and was a little lost, and through a variety of things found myself back at MIT working for the Media Lab in a group called Think Cycle and Design That Matters. And Design That Matters has spun off into its own separate nonprofit that's run in Kendall Square. Think Cycle is still a website. I'm not sure how actively it's used, but the idea was to do collaborative design work for developing countries overseas, so that someone in Kenya could post saying, I need a better water filtration system, and someone working in the US who had a few extra hours could work on that problem. Which is interesting, but as we'll talk about, it's really hard to do that kind of work without actually going to Kenya or wherever you need to go. So that was one of the challenges. But through that, I met Amy Smith and met Sally Susnowitz in the Public Service Center and became MIT's first service learning coordinator, which allowed me to figure out how to apply projects that help people both in developing countries as well as in this country, people who are underserved in a variety of definitions. Figure out how students at MIT in their classes could be working on projects that would help them. So for example, how can you learn in 2002, which is mechanics of materials, relatively introductory course, how can you actually be helping people in Haiti and figuring out projects where the activities that you're doing in class that you're learning really hardcore engineering or hardcore science or whatever can actually be helping people in developing countries too, because that tends to resonate really well with students, make the material more interesting, make you more excited to learn the material, and help people too. So it was cool, and I loved doing it for 3 years, and then I said, you know what, I really want to be doing these cool projects, not just helping people do them. So that's why I came back to grad school. And so my grad school research is in charcoal, which you'll learn a ton about in this class because it's very relevant to the class, conveniently. And then also studying service learning as a pedagogical technique in engineering. So that's in a nutshell. Do you guys have any other questions about my background? Yeah?
Do you mind sharing what year was it you were the first? What year was it when you were the first service coordinator? Service learning coordinator?
Yeah. I think it was 2002 that I started that, somewhere around there.
So far developed down that road now, and that's so recently. I mean, not that recently.
Yeah, no, MIT has changed a ton. Like, I've been here since '94. And MIT has changed a ton in almost 2 decades, in a lot of ways, and many ways that I'm quite jealous that I didn't have D-Lab when I was an undergrad, didn't have service learning, so it's great that we have it. And just to repeat that question, you were asking when I came to MIT for, and when I did the Public Service Center work. So yeah, so any other questions about that? More details about the trip we're going to talk about today. Projects from last year and details on the final project a little bit today and then more next week. Extent of work D-Lab does in developing countries. I think we work in more than 20 countries. The biggest work we do is over IAP when a bunch of students travel for D-Lab development, as well as what other classes travel? Cycle Ventures. Yeah, the D-Lab schools class travels. So there's a lot of work done over IAP. Then a bunch of students often get fellowships to travel over the summer to do work. Amy Smith and myself and Jose Gomez Marquez and some of the other D-Lab staff and instructors also travel independently to do work in developing countries. So we're working worldwide. We work on almost every continent, not Australia and not Antarctica, but pretty much other than that, we're working on it. And how we pick countries is kind of complicated and subtle, so I won't get into that, but there's a lot of countries we work in and more are being added regularly. However, we try to maintain really strong relationships with the community partners we work with, so we're not just doing one-off visit 1 year and then leave and never see the community partner again. And so, because that's not very useful for the community partner, that tends to do harm, not good for our relationship and the general NGO world's relationship to community partners. So we try to revisit, so that requires a lot of commitment. So once we have an established relationship, we have to keep going back, which means we can only grow if we have additional capacity to go back to new places. Are there any other questions about that? Just general D-Lab stuff? I think there's 12 D-Lab classes. So lots of opportunities to faux major in D-Lab if you so choose. We have some students who basically do that, or just take one and experience it, enjoy it. Yeah, there's Europe opportunities, other stuff if you want to get more involved. Okay, So that's Muddy Cards. So I will try to do that relatively quickly, but at the beginning of every day, make sure we review what wasn't clear last time. Yeah. So next, I want to talk about the lanterns. So as I mentioned, they were awesome. Here's a picture of almost all of them, and it was really exciting to see them. And what I've done is I've put them on the back walls, and so what I'd like everyone to do is take 2 minutes to just, if you haven't looked at the sheet that I gave you that gives you feedback, look at it, look at the grading rubric so you have a sense of what we valued, and then check out the lanterns and see what strikes you both in terms of the rubric is a really solid or a really weak lantern. There's nothing really weak on that table, but there's some that are stronger than others. And then also ones that just strike you as ones that are some of the best in terms of actually using them in developing countries, what really fits. And try out the switches. Some are easier to use than others or more obvious to use than others. I think when we last played with them, they were all working. Hopefully they all still are. So just take a few minutes just to familiarize yourself with them. And I will give them back to you after next week, but I need them this week, so don't take them back yet. Okay, so I'm just going to highlight some of the cooler lanterns that some of the students made. There's a lot of different form factors you can see. This one would be a personal lantern, and then you switch it on, and it has a nice reflector. There's also some that look very much like traditional lanterns. One of the things I really like about this design is both that it has a very simple handmade switch. You can see it turns on and off like that. And then also the top opens so that you can look inside, understand how it works, and if there's a problem with it, repair it very easily, which is a nice aspect of designing for any product, and specifically in developing countries where getting help for repair is harder. We also have some more radical designs. For example, this I call the lightsaber design, and the intent from the student was that it would help you light your way at night. So you could hold it as a walking stick and then also use it to light whatever you needed to light. This design hasn't been fully realized in terms of the lantern aspect of it, but the use of the binder clip as a switch is very cute, and we liked it a lot. This lantern uses a ping pong ball diffuser, which is a really nice integration of found material, very effectively used to improve the effectiveness of the light. And you can see the whole range of devices here, and we just really enjoyed seeing the tremendous variation in all the different devices with students all being given the same assignment. So the variety is tremendous, and it's really cool that you got an assignment to all make a lantern, and I really can't say there's any two that look the same, not even close, and part of that's the reality of found materials and us all being different people, but it was nice to see that range. And so clearly there's not a mental conception of lantern that is so rigid that we're all going in the same direction, which is pretty cool, actually, because I talked to a woman who works for the World Bank focused on lighting in Africa, and they've really pushed lately for better lanterns in Africa because 10 or 15 years ago, all the lanterns basically looked like Coleman camping lanterns because that was the designer's conception of lantern, and that's what they built, which is a really limiting, problematic situation for the whole different range of lighting needs in Africa. And Africa is itself, we talk about it, and it's a continent, right? So it's sort of, and it's a big continent, so it's sort of like talking about the needs of Americas, including North and South America, and saying, oh yeah, we all need the same exact shoe, right? And no one in this room is even wearing the same shoe because we all have different needs just within this room, and we're a pretty uniform community in some respects, right? In other respects, not so much. But in some respects, very uniform, and yet we all need different shoes, and similarly, we might all need different lanterns. And so if you abstract that to, or expand that to all of Africa and all the different lantern needs, that's huge, and yet all the lanterns are looking like Coleman lanterns or kerosene lanterns, is very limiting. So I was really excited to see the range. What else did you guys notice?
The switches were pretty unique.
Yeah, the switches were unique. Some were very easy to understand, easy to use, both handmade and off-the-shelf ones that were grabbed. Others were pretty subtle and hard to figure out, is what I saw. So there was a real variety there. And after class or during the break, you might want to go back and think about what made for a great switch and what made for a subtle switch. I know, like, for example, this lantern, the person wrote in their write-up intentionally that they have the switch right here to turn it on. Ooh. And it's not working anymore. Oh, it is? Oh, okay, it is. And so they said, oh, but that looks kind of ugly, so I'm going to add these wires here so that the aesthetic is a little bit better, which is a really nice thought, except the result is that the switch is really buried. So you have it took me quite a while to figure out, without reading the instructions, and I didn't read the instructions unless I had to, how is this going to work? It takes a while to figure out. And there is a realm of design where it's appropriate to make things subtle. But for the type of design we're going to be doing, where we're working with people who are almost definitely not going to be reading instructions, and a variety of people are going to be using it, you always want it to be very evident how the device works, so that people can use it without instructions. Anything else you guys noticed? Yeah.
I guess like when I approached the project, I was like, okay, so she wants a lantern, not a flashlight.
Mm-hmm.
And so like the challenging part was using, I think we're all really resourceful because there's like Laverty's cups and there's like an eyeglass, like a case for eyeglasses. Yeah. So that's really fun to see. And so it was challenging, like I really wanted to like meet the expectations of the assignment,
Mm-hmm.
but it was so broad that I was like, oh my God, what she wants to do? Should it be like channeled in one direction? Should it
Right.
be like radially? Oh my gosh. So I don't know how limited we're going to be in our design in like these developing countries, but
I think this is very real world, that no one says, I want a flashlight that looks exactly like this.
Right.
And even if they do, they rarely mean, and if it looks exactly like this, I'll be happy with it, right? Because when you're not a designer or an engineer and you're talking about a product, it's really hard to talk beyond what you've seen and what you've experienced. And it's rare that what you've seen and experienced is sufficient for what your actual needs are. So part of the challenge is, how do I dig down, ask the right questions, talk to my users to really understand what they need as opposed to what they say they need, which may or may not match. And while you really want to respect your user and their requests and really understand the impetus behind all their requests, some are really confusing to you and really legitimate. And others are really confusing to you or really clear to you and not entirely what they mean. So for example, we were just talking about this the other day in D-Lab, that oftentimes women who spend a lot of hours collecting water and or collecting wood value that time because it means they're away from their family, they get a little break, it's the only time they get away from the house, and they get to hang out with their friends and go for a long walk. And that can be a really nice thing. And so eliminating that time without building in the other opportunity for that socialization means they've just lost a key part of their daily life that they value. And so they may say, oh, well, thanks a lot for making this more efficient stove or whatever, but I would rather keep using my old one, not because I don't like the new efficiency or the new lack of smoke, but because I miss the time with my friends, and that's so important to my mental health and sanity and well-being that I'm still going to go collect the wood. And so there's a million examples of why projects like this fail, and so it's really important when you're talking to users to understand all these subtle elements. And so if someone, might very offhand mention, it's nice to talk to my friends, right? And if you don't pick up on that as a huge need, you may design something that's going to flop for that reason. And so here, you didn't really have a chance to talk to any user, right? I just said, make a lantern. But that is the open-ended sort of thing that you often get from customers. So yeah. Okay, so overall, yeah, great job. You got the specific feedback. Yeah. Okay, so are there any other questions or comments? Okay. So I just wanted to do a little review on the human power stuff. So you guys all got to try out the tump line. You can see where it actually goes on your head varies. These are both cloth tump lines. I've seen them made out of bark, a variety of things. Yeah, but you can see the absurd amount of weight that you can carry with a tump line. Like these are full Coke bottles, and that is really a ridiculous amount of weight. And there's the lab assignment includes reading up on these a little bit more, so I'm going to let you do that and not talk about them right now. But they're very cool. Did you have a question?
How long do we walk with that?
All day. Yeah. And then the head carry, so you can see the variety of devices. There's not a huge variety, but you do see like both the jerry can and a more traditional water carrying, and you see all sorts of ridiculous things or amazing things on people's head. And the thickness of this fabric part that separates your head from whatever you're carrying really varies depending on cultural norms. So you'll see a whole range from like you can barely see it to something like this, which is quite thick. We use quite thick just because I find it easier, and I figure you'll find it easier too. It's pretty normal to get help bringing it up and down, so getting that help wasn't a cheat, but it's also pretty normal to be using no hands, and none of us were able to pull that off, unsurprisingly. One thing we didn't really talk about is pedal power, which is a huge part of human power. And that's a little bit of your assignment too, so I'm not going to go into that too much. But, and this whole thing is from Jody Wu, who was one of those D-Lab majors I talked about, who took as many D-Lab classes as she could take, and is now working on a company. She owns a company in Tanzania doing pedal power devices that came out of her D-Lab work. So, and there's a whole variety of people where these pictures came from. But so pedal power all the way from the bicycle, which you're used to a completely home-built bicycle, which would be rather challenging to ride, but is pretty amazing, to something sort of like a bicycle, but is just basically using wheels, both for going down hills and up hills, because carrying loads is always an issue, and the assumption of good roads is not a good one. To a pedal-powered device that looks kind of like a sewing machine power, but instead is powering the, what is it, $100 laptop? Is that what it's called, or $200 now? I forget. Yeah, OLPC, that's it. Thanks. Yeah, this is a pedal-powered compressor, which is a kind of interesting project because pedal power is the exactly wrong technology to use here, because when the pressure tank is empty, you have to be pedaling incredibly quickly to get any sort of pressure built up because there's no back pressure for you to pedal against. And when it's full, you have an infinite amount of pressure to push against, and so you can't pedal at all. And in fact, there's a really handy device that works for this great that uses arm power, and of course you could think of a foot version, but this is just a reminder that pedal power has a near infinite number of uses, but not literally infinite. There are some places where pedal power is ridiculous. This is a pedal powered grinder, I think for corn. People carry amazing loads on bikes as well, and these are bikes specially modified to allow for carrying loads. We usually think of pedal power as two-wheeled bikes, but three wheels is really common too and can offer a lot of stability benefits. Pedal-powered ambulances. There's a lot of places in this country and more so in Europe where pedal power is standard, in more developed countries as well. And we're seeing it more in Cambridge, actually. There's a lot of pedal-powered delivery now in Cambridge, which is kind of cool, though harder right now in this season with all our snow. Variety of folding bikes or different orientations of bikes. A variety of different things carrying. Amazing bikes for going on water. These are pedal-powered washing machines that were, I don't know about this one, but there was a collaboration between D-Lab and a group in Guatemala that does pedal power to build a washing machine. Pedal-powered water pumps, coffee depulper, maize sheller, washing machine, blender, plow, knife sharpener, soap blender, nut sheller, saw, more washing machine picks. This is the group in Guatemala. Maize grinder again, woodworking lathe, corn shelling. So there's a ridiculous number of ways to use pedal power, and because most of you hopefully have ridden a bike, and there's a lot of technologies in D-Lab that are more familiar with pedal power than like the pumping that we showed. That's why we went for pumping rather than pedal power. But it is something to keep in mind as you're thinking about projects, that pedal power is pretty powerful and awesome. Any questions on that? Okay, so now we're going to talk about power generally. And one of the biggest challenges is that power is really generated where you need it or when you need it. So for example, the sun is only out for some portion of the day, and in the winter in New England, even less, and in Norway, where my brother lives, even less. And on super cloudy days, it's a whole lot less useful. So that's a question of when, and that's true for wind as well. The when is an issue. And then the where is an issue. Very few people want to live right next door to a nuclear power plant or a coal-fired plant, nor is it preferable to. And for like microhydro systems, you may not want to live right on the river. You may want to live a bit farther. So what are the solutions that humanity has come up with to address that issue? Yeah, so we have grids. Yeah, which include transmission lines.
Ways to store the power and transport it.
Yeah, and then we have storage and transport. Absolutely. And so we're going to talk about both of those today. And so what are the limitations of grids? What are the challenges you face with any grid?
It's difficult to actually set up a grid, a large-scale grid.
Yeah. So, but what do you mean by difficult?
Well, it's very money intensive if you want to string up a highly efficient grid. The main reason why the U.S. is actually still working on a grid system developed like 100 years ago.
Yeah, so grids are incredibly capital intensive if you're doing a big grid. One.
Change the voltage as you go across. You have to increase it for long distance and then decrease it back to usable power.
Yeah, and do you know why you have to change the voltage?
Efficiency.
It's enough for efficiency when you're transporting it through the...
Yeah. So you have loss issues that you need to take into account. I saw a lot of hands, yeah.
It's still really inefficient, even with that conversion, because like they just don't phase. So part of one of the smart grid technologies is the PMU, which is a phase meter units, I believe. So it tries to sync it. But reality, like today, all they have is like people at different substations and just like crank it up, crank it down a little bit, depending on how it's coming in and out.
Yeah.
But I think the problem with grids from a policy standpoint is that once the infrastructure is there, they're there for long periods of years. And so it's really hard to regulate because you have like so many different NERC regions. So these are transmission lines going across different states, then you get into the issue of like, is it the federal government or is it us? And so just like regulating a lot of policies for those issues.
Absolutely. So we have issues with once they're in place forever. That the efficiency, you can do things to improve the efficiency, but you're going to have losses always. And then policy and ownership issues are challenging as well. I saw a few other hands. Yeah.
When there's storms and you have a power problem.
Yeah, so storms and I'd say more generally maintenance for typical and atypical situations is always an issue. Any others? Yeah, let's see.
You usually have to use the energy that you generate within like a couple seconds still.
Yeah, so it's there isn't no storage in a typical grid, right? So lack of storage is an issue. Yeah, and then getting to storage and transport, and for that we're going to focus on batteries. There are a few other options, but the most common is batteries. So what are some issues around batteries?
Very limited life.
Yeah, so the life is an issue. Disposal, which is very linked to life.
According to our problem set, it actually doesn't carry that much energy, so it's not very.
Yeah, so the density, the energy density of batteries is pretty poor compared to a lot of other technologies we're used to. Any other thoughts? Yeah.
Material or like that you need to use to make the battery?
Yeah, so the materials, that can be an issue for environmental reasons. It can be an issue for cost and just availability. There are some materials we use that we literally have a fixed amount of, and we're running out. Some other things, yeah, go ahead.
One more thing with batteries is just there are design constraints as far as usually use them for small portable devices, yet the smaller the battery, the less energy it provides. So it's just, I don't know how you would say that, design problems.
Well, I don't know if this is exactly the right way to say it, but the way I'm going to say it is that the size and the weight of the battery versus its utility to you is kind of inversely proportional and a bit of a bummer. So you want, for getting a really good storage capability, you generally need a big, large, heavy battery, and typically you want as light and small a battery as possible. So that's a pretty frustrating conflict. Yeah, so let's start with grids. So all of these are major issues, and I want to start by talking about the US grid just for a minute. So this is what the US grid looks like. This is a really nice interactive graph from NPR. That the link is on the slide notes, and you can go to it and play with it. And you can see all of the different transmission lines, and all these voltages are incredibly high compared to what you're used to using, but you can see there's a range of sizes because the higher you have to transform the voltage, the more expensive it is. But you can see this is our major, these are our major currents on the eastern seaboard. So that is just an interesting thing to note. And then in terms of the power plants in the US, you can see just how spread out they are and how varying in size, and then therefore how critical our grid system is in order to get the power to where we need it. If otherwise, people in Maine, for example, would not have much power at all. And you can see other parts of the country where the power would be really limited otherwise. And then this is just, I just want to show you this because it goes down and shows you all the different plant types you can have, and then you can click on the plants. You can go to each state and compare where we get our power. So for example, in Massachusetts, we're primarily gas, whereas in Vermont, they're primarily nuclear. So it's just really interesting to see, even within the US, how much variation there is in states right next to each other, let alone across the country. You can also see what the solar opportunities are in the country, and if we're going to go to primarily solar, we have to figure out a way to transmit the power from in this realm all the way across the whole country if we're going to be successful with solar power. And similarly with wind power, some of the eastern and western seaboard look great, but then the center of the country is kind of in trouble if we just go with wind. So comparing the amount of wind power to, say, the number of power plants that are in existence, wind is a whole lot less well distributed than what we've got right now. So yeah, this is just a very cool demo to give you a sense of the US grid really quickly. Okay, so now it's time to do some equations to think about the line losses that you have to deal with. So the line losses are all due to what?
Heating.
Yeah, heating of the wire. And why is the wire being heated? Because it has current through it, and a wire has some resistance. So the equation for that is Joule's law, and is defined as Q is equal to, which is the heat, is to the square of current times the resistance times the time. So, and that's Joule's law. And if you're not super comfortable with your double E, you're probably going to say, oh, well, the IR, that sounds like a voltage, and throw a voltage in there. And you're missing a subtlety, because then you say, oh, well, it's related to current and voltage at the same level. But you have to figure out what voltage you're calculating, because if you recall, while current is going through the whole wire at the same rate everywhere, because it's a flow, a voltage is based on a comparison of two places, and you have to compare the right voltage in order to plug that into the equation correctly. So we're not going to do that right now, but we're going to go through this equation in a little more detail, so hopefully it becomes a little more intuitive. So let's pretend that we're trying to deliver power from some power plant in Western Mass to Boston. And so we're going to call that power that we need power with a capital P. And power, as we recall, is the voltage, and that's from the line to ground times the resistance through the power line. So P equals VI, but we also have the issue of the power loss that we know is happening through the wire. So to calculate that, you're using the same equation. We're going to call that lowercase p is equal to voltage from the end of the line to the beginning of the line, so L1 to L2, times I. These I's, thankfully, for just thinking, for minimizing how much confusion, are the same I, right? They're the same current going through the wire, which is going to be the same throughout the entire wire. But the voltage here for big P, we're worrying about checking the voltage at one end of the line or the other to ground. And little p, we're worrying about the voltage drop from one end of the line to the other. So for example, let's say the power plant is providing 10,000 volts. And where on the board can I write and you can still see? Like if I write down to there, can you see it? No? No is a better answer than blank stare. So, all right, can you see this range? Yeah. Okay.
They said storms and maintenance if you want to draw lines.
Okay. And this is going to make me batty. Okay. So we have 10,000 volts. So the power, the voltage here from line to ground at the power plant is 10,000. And then let's say we lose 1,000 volts across here due to line losses. So this would be this V, and this would be V L minus G. And then conveniently, so then we know what we have, the V at the end is just going to be 9,000 volts, right? So this is pretty simple math, hopefully. So power, the lowercase p, is equal to the voltage drop across the line. So V L1 to L2 times I. And yeah, sorry, I'm getting myself confused. So power is equal to I, and power is also equal to I squared times R, that I. So our options are, we can make our V, sorry, I just got totally lost in my notes. So let me start again. Right. Okay. So we have these two equations. We're not going to worry about numbers right now. So we want to maximize this P and minimize that P, right? So, and we know the relationship between these two V's, right? So then, so if we minimize I, we minimize that power, which is good, but we also minimize this power, which is bad. And that's why we're trying to pop up the voltage to be as high as possible, so that we can maximize power and minimize our losses. Does that make sense to everyone? I know I got lost in the middle. Okay. If it doesn't, and you don't want to talk about it right now, you can talk to me after class. We can go through it then. So that is great in a macro grid, right? So we can bump up the voltage, super, and we're all set. However, in a microgrid, bumping up the voltage, transforming the voltage is really, really expensive. So in a microgrid, you don't do that. You just use your given voltage, which saves you a lot of money, but also means that line losses are huge. And so in that case, if you can't change your voltage, what is your loss based on? You already answered it. It's the resistance in the wire, right, is what we have to worry about. So the resistance in the wire is based on rho L over A, where rho is equal to the inherent resistivity, L is the length, and A is the area in cross-section of your wire. And so for your resistivity, that means you're picking your wire. So you could use an aluminum wire or a copper wire or what have you. Copper tends to have the best resistivity of the options, but copper is also incredibly expensive, which you know if for no other reason than because people are stealing copper all over countries in the US. So people who have beautiful rain gutters made of copper no longer do, because people are stealing them because copper is scarce and expensive these days. Length, so copper, your resistivity is probably going to be basically fixed based on your costs. Length is something you can control, but is also a bummer, right? Because if you go too far, if you want to power a house that's an extra few blocks down, you can't if you're limited by your length. And then your area, your diameter, again, is going to be completely related to cost. So from a cost standpoint, you want a really small area, but to minimize your resistance, you want a really large area. So yeah. So let's run through a calculation just to hopefully make this clearer. So in teams of a couple of people, if you can run through this. So typical jumper cables are are helping to provide a jump to a dead car battery from an existing working car battery, right? So you're providing somewhere on the order of 400 amps at 12 volts, and the typical diameter of a jumper cable is a wire gauge of 4, which translates to 2/10 of an inch in diameter, versus a typical wire like you used on your lanterns is on the order of a wire gauge of 26, which is a much, much, much smaller diameter. And so we're going to assume we're using copper, so that's the copper resistivity length. And so now what I want you to do is figure out what length of cable can be used for each wire gauge, so that you still, so that your losses don't dominate over your transmission. Does this question make sense? I'm seeing a lot of confused faces. Yeah? Yeah. So let's say we can't lose. You can define how much you can lose, because again, this is open-ended, but intentionally open-ended. But if you're losing 100% of all your power is going to heat, that's a problem, right? And why don't you set what percent can go to heat, and then figure out what length you can use? Okay, so I think most people are done, so I'm just gonna get a range of where we are in the class. So can someone just shout out what you got for the 26 gauge, the 4 gauge, and the percentage loss you assumed? Like, I know you guys.
0.055.
And another team?
0.01. Oh,
10.
yeah, 10 there. 33. It's also 0.1 for the first one.
Yes.
Yeah.
No,
0.1.
it's centimeters.
Yeah, which is 0.1.
No. Yeah.
Yeah.
Anyone else?
About 9 centimeters. So, and what is it? 14.6 meters.
14 meters?
Yeah,
And
for 40%.
So these are all looking, there's clearly something subtle going on where we're not getting it quite right, but we're all the order of magnitude correct. So I'm happy. This class is not about getting an exact answer, but getting the gist down, and this looks good. Is there a team that got wildly different? I think there's at least one.
We got 0.36.
0.36 meters, and what?
We didn't calculate the.
Okay, and what was your percent loss?
33%.
5. 1/6.
I'm sorry?
33%. Okay. 33%.
33%.
No, it wasn't. It was 1/6. It was
Sorry, no, it's 1/6. It was, we lost 2 volts out of 12 volts. That's 1/6.
No power loss.
Is it power? Is it according to power loss or voltage?
Same
It's
thing.
the same.
That was IV. That was linear.
Yeah.
So what's
Okay,
1/6?
Never mind.
It's like 18%.
Okay. So basically, this is on the order of a length of a jumper cable is usually between 2 and 3 meters, and these are all really big losses, right? Like your wires are going to get super dangerously hot if you're losing this much power. So, which is fine for just doing an order of magnitude. Where am I? But that's why they're actually quite a bit shorter than that. Plus, you rarely need your cars to be 20 meters apart, thankfully. When you do, it's really frustrating. And then this is a reason why jumper cables are expensive, and you need a big diameter copper wire, right? This just wouldn't work. And so if someone, again, consultant came to you, or someone came to you looking for money saying, I have a great idea for a new jumper cable, and we're going to use really thin wires, it's going to save us so much money, you can do this type of calculation really fast and be like, oh, no, you can't. Unless you want to have magic cars that are right next to each other. So, yeah.
If you want to extend it to be 20 meters away, and so you just put like 2 jumper cables lined up, there isn't supposed to be a loss there, but do you know like what the actual loss is when you like just connect wire to wire for this kind of power going through it?
Well, so if you connected, if you have your one car and your next, excuse me, if you have one car and your next car and you're connecting your jumper cables, and then you say, so that's just going to work, right? Because it's normal jumper cables. But then if your car is in fact this far, so you need another set of cables here, your loss is going to go up, right? Just because the distance is going up. Yeah.
And the contact like loss, is it like with a calculation?
The loss associated with your contacts?
Yeah. Is there a loss? Do you know what I mean? Just like clipping one to the other.
Yeah, there's going to be losses everywhere, but I would say the length is going to dominate over that. So again, this is the type of engineering where you focus on what's going to dominate and pay attention to that, and the stuff that is small you don't even worry about, which is most of engineering until you get into the super detailed design. Yeah, so you worry about it. And one of the things that's really interesting on your lanterns is that a lot of you didn't use wire. You used found materials like paper clips and I can't remember the name of binder clips and all the variety of things which have decent resistance, and yet you have an LED that's pretty robust to high resistance, and so it worked fine. So that is one of the nice things to think about is, yes, you're getting losses there, and if you want to get if you want to perfectly maximize the light output of your LED, then you need to worry about it. But if the losses are relatively small, you're fine. So if one of you had made a lantern that was like, somehow had wires that were 20 feet long, then we're going to start worrying, depending on how small your gauge is and how high the resistance is in the line. But you've got some flexibility there. If you guys didn't, if anyone got lost here, which is understandable because it's confusing, and just come talk to us and we can go through it with you. But it's important to understand this because it's a useful calculation to be able to make. So just in summary, for microgrids, some of the benefits are autonomy, right? So if a community in the middle of nowhere needs power, you don't have to wait until the government decides to deliver that power to you. You can just build it, and you're not reliant on vagaries of politics. You can just build it. Compatibility, microgrids can hypothetically attach to the macro grid, so that's an opportunity. And you can connect your with some controls, you can connect your wind turbine and your hydro turbine and your solar panels all to the same grid, and you've got some compatibility and flexibility opportunities there, as well as scalability within the limits of what we just talked about of transmission line length. You can scale your microgrid, so you can build it small and then expand it as needed, as long as you're paying attention to your limiting factors. Some of the challenges of microgrids, especially in developing countries, are there's always going to be maintenance, and if it's not run by a utility, then it's a local issue of the maintenance, and so who's going to do that, and are they going to do it well? Limiting loads, so in the US, we have our fuse boxes that limit how much power we can draw. You don't always necessarily have fuse boxes on a microgrid, and so or you don't have ones at each local house because that's expensive, and so people might just start plugging in stuff willy-nilly, and then you take down your whole microgrid. And then also just private versus public sector issues. There's both issues of that one of our community partners faces in Nicaragua, where they build a microgrid and then for whatever political reason, the government decides to install the public grid, and all of a sudden all that investment of the microgrid goes to waste unless you can tie in your microgrid to the public grid, which rarely can because of a variety of political and technical challenges. There's also issues sort of that I referred to of if it's locally owned, all those sort of built-in bureaucracies that actually can be very helpful aren't there, and figuring out how to manage that. But microgrids do allow you to put power in the middle of places that would otherwise probably never get it, or it's going to be another century before they do. So it is pretty valuable. So with that, let's take a 10-minute break, and then we'll talk about batteries and the trip. This graph should look familiar both because I showed it last week and because you made a vaguely similar one, hopefully in your homework today, for today, that batteries are kind of brutal, right, in terms of the energy solutions we're used to. And just as a good rule of thumb, batteries are in the order of 10 to 10 to 0 megajoules per kilogram. And you probably won't memorize this, I haven't yet, but there's 0.278 kilowatt hours to 1 megajoule. But if you can get that in your head, it's useful. So, and capacitors, which are another way that we store and have even worse life, are also even worse in terms of use. And then springs, which students often suggest is a great way to store, and there are some radios and wind-up flashlights and things like that that use it, we're talking an even further order of magnitude of badness. And fossil fuels are somewhere on the order of 10 to the 1. So again, this is why batteries are frustrating to use, but useful. So the other thing that, so now talking about batteries, there's a lot of different chemistries of batteries, right? And more being developed every day. And we are going to be likely sticking with established technologies because the third dimension on this graph, which isn't shown, is cost. And emergent technologies are way off the chart compared to, say, a lead acid. And lead acid batteries for a lot of the systems we're talking about are still really expensive just because our costs were so constrained on cost. So alkalins are common and are relatively inexpensive, so they're a great technology, but their bummer is that they're not rechargeable. And so you're replacing them constantly, which is a huge waste issue, so that increases their effective cost. Yeah, so one excellent battery resource, just if you're trying to figure out batteries, is this battery primer put together by David Wallace, who's my advisor and teaches 2009, which is the senior capstone design class. And I stole this just summary page from that document. So when you're worrying about batteries, there's a ton of different things you have to worry about. So, and some of which we talked about already. So the physical characteristics, the size, the shape, and the weight. It's really frustrating when you need to, for example, power an LED. You noticed I gave you 9-volt batteries instead of AA batteries, right? Even though AA's are what you're more familiar with, but AA's don't have the voltage you need unless you connect them properly. But AA's are a much nicer form factor than 9 volts, right? But you're limited there, and it gets more extreme the more you go into a variety of batteries. All the different voltage issues. We're really talking very simplistically, but when you really get into batteries, figuring out exactly what your peak load is, how much time you have, your current, it all matters, and it can get complicated. But the good thing is there's really great handbooks out there that explain it all. Batteries are really well documented. If you get a battery spec sheet, you see all the graphs, you can figure out exactly what you need. But you do have to realize going into it that you have to consider all these things, and you can't just grab a car battery and use it and expect it's going to work well. So for example, a car battery as opposed to a deep cycle lead acid battery, both are lead acid. And one of the differences is that a car battery, you need a high current for a very short burst of time just to get the starter motor to run, and then your car is set, and then you can recharge it. So thanks to your alternator when you're driving your car. So the car battery almost never discharges unless you leave your lights on all night. Bummer. And then your battery's dead and you probably need a new one if you do that a few times. Whereas a solar panel installation or wind power, if you think about it, you don't need a really high current quickly. You need a steady current for a long period of time. So a car battery's chemistry is not, it's not made to provide that type of power. So if you try to use a car battery, you're going to kill it really fast because you're discharging it too much. And all batteries have some lower limit of where your discharge is, and you can't discharge any lower. So that means if you're doing anything complicated, you can't just use a battery. You also have to use some sort of charge controller or discharge controller so that you never discharge your battery too much and you never overcharge it, and all these subtleties. So batteries are really useful, but there's a lot of details to worry about. So again, as we're talking about the duty cycling, the charging, and the discharge cycling, temperature is another thing. We're generally working in climates that are really hot, and batteries are ideally used in a pretty warm environment, but not 100 degrees. And so they don't always work well. 100 degrees F in places we're working, and so you have to account for that. Service life, so how long do they last, and is there going to be someone and some budget to replace the battery when they die? Safety, we're all used to alkalins, right, which are pretty safe. They rarely leak, but a lot of the deep cycle batteries can actually be relatively unsafe, and you need to worry about them. And all batteries, you have to worry about disposal. Environment, maintenance is a huge issue on the cheapest lead acid batteries, which are what is often used, and then the cost, both initial and life cycle. So there's a ton of stuff to consider with batteries. And then for just simply thinking about, say, a lead acid battery and how it's going to integrate into your system and how do you size it. So you figure out what your source is, and you have to think about both your daily average as well as your peaks and lows on a day-to-day basis and a seasonal basis. So if you think about solar, it's varying over the season, it's varying over the course of the day. Your daily average of your load, and that also varies. If it's hot, people might have more fans on. If you have a party and you keep your lights on for longer or what have you. How many days of storage? So if you have no days of storage, you're just relying on the sun and you have a cloudy day, it doesn't work. your system doesn't work that night. If you have a few days of storage, great. So that typically people put in 3 to 6 days, depending. And then you also have a budget. So you can develop the perfect battery plan for what you need, and then you realize that that's going to cost you $10,000 and you only have $1,000, and so then you iterate and figure out, well, what can you pull off? The things you're considering are your energy source, and usually for renewables, that's a DC source. And then you have a charge controller to make sure that you don't harm your battery as you're charging it. And the charge controller has some efficiency. The battery can never get too low. And then you have an inverter to go from DC to AC current, and that has an efficiency all the way to get to your AC load. In some places, like for example on boats, they just use DC lighting, and everything is, on certain boats, everything is just DC, so you don't have to use the inverter, and that's an option too. But a lot of people want appliances that are not DC appliances because those are a limited set. So they're all just different issues to consider. So now I want to, are there any questions on batteries? I know this was ridiculously fast and limited, but it's hard to it's more interesting and useful to talk about the batteries once you know what you actually need. And so that's why I'm trying to just give you the resource of what you might need to think about and where you can go to think about it. There's also a handbook that David Wallace references, that's where he got all of that stuff. That's really good, that's on my desk today, so you can look at it right now after class if you're interested, but then it's going back to the library because it's due today. So, but you can check it out from Barker. There's lots of resources. So are there any questions on batteries just generally? Okay. So now what I want you to do is 2 estimation sets, again in groups, and again trying to vary who you're working with because you don't know who you'll be going on the trip with if you're going on the trip and who your team will be with post-trip. So it's nice to get a sense of everyone in the class and get comfortable working with them. So one is estimating the power required for typical objects that you might encounter in your daily life. And then probably building off of that estimation is each person doing a separate one, but you can work together to help you figure it out, how much you think you consume daily. And everyone needs to get how much energy you consume daily. And everyone needs to get to the personal daily energy consumption number. You need to get a number. This will probably take like 15 minutes to get to that number because this is gonna be related to the homework. So everyone needs to turn in a number to me, and I'll have a sheet going around so everyone can write down what you think your personal energy consumption is on a daily basis. And again, I know your days vary. Some days you cook with an oven and some days you don't, but some random average. Any questions on this?
For the daily energy consumption, say you buy food at a store for a day, or you don't cook, should you like kind of estimate, I guess for my meal, they probably cooked it in an oven and it probably took this many watts, or
Yeah. So just a general guess. Okay. This is a challenging assignment, right? Because it's really, there's so many times that you're dealing with energy that is out of your control, right? That's the majority of your life is energy that you have no control over. This building is often 85 degrees, and that wasn't something you chose or something I chose, but there you are. And what percentage of this building is your fault? Like, that's a really strange thing to think about and calculate. And so you just do your best. The other thing is you should only be talking about consumable energy. So you don't need to worry about the energy required to build your laptop, just the energy you're pulling to power the laptop as you're using it that day. Does that make sense? Any other questions? Okay, so get started. Now you're here if you have questions. So I see a few orders of magnitude variation in what you guys put. So this is actually part of your homework assignment. So definitely you'll want to go back and do some sanity checking on your number. And then also, just naturally, there will be some refinement when you do it for your homework. But yeah, make sure you know what number you just wrote down because you're going to use that in the homework to compare it to the value, recalculate, etc. But I'll talk about the homework in a minute. So now, are there any questions on this? All these numbers and whatever else you used, it's relatively easy to Google. So I wanted you to first do the estimation, so you got to practice with estimation, but now you can just Google it and look it up. I recommend when you Google to look for at least 3 corroborating sources that have different, that aren't self-referenced before you trust it if you're going to do Google, because as all-knowing as Wikipedia is, it's often off, and so are other sources. So Google's fast, so if you're not going to get a real reference text, then that's actually believable, then definitely get a few sources before you rely on it. Okay, so the spring break trip, you guys of course had questions about it. So we're going to Nicaragua, which is south of here. So spring break is this week, and we try to go Saturday to Saturday. But because of plane ticket costs, sometimes we travel on a Friday or Saturday or Sunday on both ends. So I will put up shortly a form online for you to tell me, like, would you be available to travel on a Friday? Some of you might have classes after this class, in which case that would be no. Some of you don't. And so students who didn't last year just skip the day of class, this lab on the Friday, with my permission, obviously, to fly to Nicaragua to make it more affordable. So one of the questions on here will be like, what is your flexibility so for arriving and departing, so that we can minimize plane ticket costs for ourselves. But those are the approximate dates. The cost for you, so for all D-Lab trips, students contribute $500, which usually does not even cover the cost of the plane ticket. But allows us to make it possible for most students to travel who want to. If $500 is personally prohibitive for you, you can come talk to me and we can see if we can get you a scholarship for the trip. But otherwise, it really allows D-Lab to do a lot of great stuff, to have your contribution that we couldn't do if we paid everything. Also, like, $500 is an amazing bargain for the trip you're going on, and it's nice to have you, personally contribute to what you're doing. And then also, we don't cover things like medical. You'll need some vaccines at MIT Medical probably. Those cost a little bit. We don't pay for those. If you need a passport and or a visa, that's something you cover on your own. Then when you're in country, you pay for your own food. It works out to usually a few dollars a day, so it's pretty affordable compared to here. And then we usually give gifts to our community partners, and that's something that comes out of your own pocket. They're generally very modest, both because of our own personal budgets, and it's pretty, it leads to some uncomfortable situations that we'll talk about later. If you go to this place where people are earning $2 a day and present them with something that's worth a ton of money, it's problematic for a lot of reasons. So it's not prohibitive, but those I'm just trying to make sure you guys are clear on all the costs. But we make sure that you get there with the plane ticket, housing, transportation, all that stuff is covered. Do you have any questions on the costs? And the way you pay this is you can write a check to D-Lab generally. It's pretty easy.
If you have a U.S. passport, you don't need a visa?
You will not need a visa if you have a U.S. passport, and many other countries don't require a visa. Some do. The cost of the visa, I think, last year was on the order of like $80 or $90, something like that. We can figure it out. So things to do now. There's a lot of things that need to be posted tonight, so you can't literally do it right after class. But one is there'll be a form online just to get details if you are hoping to go on the trip. That you should fill out ideally before Friday's class. 2 is check your passport to make sure it expires more than 6 months from March, because if it doesn't, you'll need to renew it, because you can you're sometimes barred from traveling if your passport expires too soon, because they don't trust that you'll be able to get back into your home country, and they don't want you stuck in their country. So we need to make sure that it doesn't expire. And if it does, if you process it now, it's a whole lot cheaper than if you have to do it like the night before, and a lot less stressful, which is why to check now. You need to make a travel clinic appointment at MIT Medical, or you can go to a different travel clinic if you prefer, but MIT Medical is easy and they're experienced for your vaccines. There's a variety of things you may need. One thing I would encourage you to talk to them about is whether you want to do malaria or not. Malaria meds have some side effects that have bothered students in the past, so some people opt to risk it. The risk of malaria is relatively low in Nicaragua, where we'll be, but it's non-zero, so it's up to you and your doctor to decide where you fall on that cost-benefit ratio, but it is something to discuss with them rather than just taking it immediately. And then make sure make sure they give you a prescription for Cipro or a similar antibiotic, so that if you do get sick in country, you can take an antibiotic without having to find a clinic that has it, which can be challenging. But that's standard. They'll do that at MIT, but in case you go somewhere else. And then the other thing is to figure out ideally by Friday, because the sooner we buy plane tickets, the more affordable they'll be. If you're prepared to commit to the trip, and if you're going on the trip, we're really expecting that you're committing to the class as well, because we're investing a lot in you to take you on the trip. And so while drop date is after the trip and you could drop it, we're really expecting that you won't. So it's on your honor. There's nothing I can do, but you do need to commit. The other thing is, if you commit to the trip and we buy your plane tickets and then you back out, you will be responsible for the cost of the plane ticket, which is on the order of $600. Yeah, so you do need to decide, am I doing this, am I not? And then I'll post the packing list again tonight or tomorrow. You obviously don't need to start packing today unless you're incredibly, like my mother, who packs months in advance. But it is helpful to just see, like, oh, I don't have any summer clothing right now that I'm willing to bring to Nicaragua and probably have trashed, so you could order it now rather than figuring it out the night before, and just start thinking about that. Are there any other questions about the trip that I can answer?
As far as like, I mean, obviously I'm not packing now, but for clothing and stuff, what's appropriate there?
Yeah, so you want to be relatively conservative, so you don't want to be wearing like super thin tank tops and stuff. Sometimes it's okay to wear a tank top. Oftentimes you want to have at least your shoulders covered, and then you wouldn't want to wear any short shorts, but stuff that comes down below your knee, or skirts and pants. Nicaragua is pretty chill about this stuff compared to some places that DLab goes. So you don't have, women don't only have to wear dresses and things like that, which is a nice thing about Nicaragua. But we do try to be dressed conservatively. And one of the things students sort of questioned last year is they would see people on the street dressing entirely not conservatively, and what's going on there. And it's because when we're in more rural areas, number one, there's a more conservative culture. Number two, and we are going to pretty rural areas. Number two is that we are representing MIT, the United States, et cetera, et cetera. And so we don't want to be on the edge of things that people might find offensive, even though some other people might wear it, right? We want to be looking as professional and respectful as possible. So even though you might see people wearing stuff that I specifically said not to wear, there's a reason I said that. It's not just because I'm uptight. It's because I want to make sure that we're presenting a respectful face to our community partners. It's really hot in Nicaragua, so you definitely want light clothes as possible. Like, we recommend people bring like a light fleece because it might get cold at night, but oftentimes it's never used. Other times it is. Nicaragua doesn't have a huge seasonal variation, but it still varies a bit. You'll definitely want a swimsuit, and again, something on the more conservative side is better than a Brazilian bikini for this trip. Any other questions about that? The purpose of the trip, which I completely skipped over, seems like a relevant thing to bring up. So the main thrust of this class is the projects that we're going to be working on. And I'll talk more about them next week, but they're projects that are beneficial to our community partners, ideally are beneficial to a broad scale of people, so that we're working specifically with a specific client, but it's not just hypothetically a one-off. It could have greater impact. And so the idea is that starting next week, likely, you guys will be working to start thinking about those projects as part of the homework, and going through the very initial stages of the design process, so that when you're in country, you can talk to them about, hey, this is the idea, what we're thinking about, this is what it'll look like, what do you think about this, give me feedback. And so that way you can really get a lot of information very quickly that is much, much harder to get if you don't travel. So that's the idea, as well as just to be familiar with a different country and what life is like there. It's a pretty great experience for most people that really enriches your educational experience, just period, to get to travel to a developing country and see how great and how challenging life can be in a different place. So it's both from a project standpoint and a general standpoint. Jess?
Maybe this I can ask you about after class, but could you talk a little bit about the security and safety issues going to Nicaragua?
Yeah, so Nicaragua, the people I know who go down there, or who live and work down there, consider it comparable to any place in the U.S. that's relatively, on the dangerous side. So that is no more dangerous than like spending time in New York for New York City or something like that. It's different, right? Like, you probably don't speak the language as well. You're not familiar with things, so you have to be more on your guard than you might be in New York. But in terms of actual dangers, it's relatively low. There have been some issues more recently in Managua, the capital city, with people like kidnapping scams with taxis, where you don't know, or you get into a taxi and then they mug you basically. So we don't use taxis that we where we don't know the taxi driver personally, and we have a lot of connections in Nicaragua, which allows us to maintain your safety. So what we do is we take all reasonable precautions. Can I guarantee that nothing will happen? Absolutely not. Do we help prepare you to make sure that we minimize the chances of anything happening? Definitely. And I think chances are good that you will come back with all your belongings and everything intact, no problem. But of course, I can't guarantee it. Just as I can't guarantee you won't get mugged walking home to your dorm tonight. It's just, you know, a reality of life. But it is relatively safe. You can go on the U.S. Embassy sites, I think it's U.S. Embassy, U.S. government sites, to sort of read up on what they recommend about travel in Nicaragua and what are the specific dangers if it's something you're concerned about. But I've traveled there 4 times last year, and I brought expensive equipment, though I was very good about only taking it out when I was inside a secure location and keeping it very secure, and nothing disappeared. I had no problem. I had a student this past summer who was there, and she had $30 stolen out of her shoe or something like that, but that was fine. So we've never had something more significant than that, but it is always a risk. Yeah.
Where in Nicaragua are we going?
Yeah, so I'm still figuring that out. Last year, we worked in near Ocotal. So Managua is the capital city where we'll fly into. And so last year, we flew into Managua. One group worked up in Ocotal. One group worked in Bluefields on the Atlantic coast, which is a very different population than the Pacific coast. The Atlantic coast has a lot of Caribbean influence as well as indigenous populations at a high level, and so it's a really interesting part of the country, but it's very expensive, so we may not be able to afford to go there this year. So we worked in Ocotal, in Bluefields, and in the Matagalpa area. We may go to Jinotega this year as well, and the way it works is that you're on a mini team, and the team goes to one place. So last year, one team went to Bluefields, one place to Ocotal, one team to Matagalpa, type of thing. So I don't know exactly where we'll be going. It'll be relatively rural, and yeah. So it's not a great answer. It's sort of real time figuring it out with our community partners right now. So as I know more, you'll know more. So the Poor People's Energy Outlook, was it helpful? Was it surprising?
I thought the focus on like opportunity cost was really interesting. So like energy is like a huge time sink, like providing energy for themselves, where energy access is poor is like just a really big deal. And I was actually pretty surprised to hear you say that it was like a leisure activity to like collect wood.
So it's both a leisure activity and a huge hassle, right? It's a combo. And so the issue is, would most people prefer not to be carrying 65 pounds of wood back and forth for a few miles every day? Of course, absolutely. But is there an aspect of that that's important culturally or personally? Yes. And so when you're eliminating that really huge burden, you have to consider the positive aspect of that burden, and how do you make sure not to destroy that positive aspect if it's too important to a community. So it's again, we're in very gray realms where I did not mean to say, if I did say, that it's a leisure activity that's fun and everyone would love to carry 65 pounds of wood every day, and frankly, why aren't you guys doing it? Because I highly recommend it, and I've been starting to do that myself, of course not. Right, however, if there is a reality that women in developing countries tend to just live at home, and you take care of the kid, you take care of the fire, and you take care of your home, and that's it. And the only opportunity you have to socialize and get a little sanity time is through work. And so if you eliminate that work, hooray, but if you don't then build in some other way to get that sanity time, then maybe people won't be willing to take that work elimination, depending on the cost benefits. Yeah.
Is that actually the concern for developers, the lab mentors? Because I feel like that's how we got where we are today. We don't
chug around 65 pounds of water, but 65 gallons of water or whatever, but we do have other hobbies or have other things that have occupied that time.
Well, so the issue
Because
is
it
not.
didn't seem to come up in the reading, so.
Yeah. It didn't come in the readings. So there is no reading, and there is no person who's the expert on all of this infinitely and can give you every insight, right? That's why I'm going to give you a range of readings, and you're going to hear my perspective, but I'm also giving you readings, so it's not just my perspective. The issue is not ensuring leisure time necessarily. That's not what I'm trying to say. What I'm trying to say is that if there's something about this activity that it's a really sucky activity, but there's this really important aspect to it that people really value. If you provide them an alternative to that sucky activity that doesn't address the part that's important to them, they may not adopt it, regardless of how hard you work, right? So I don't know if I mentioned this, but like there's the classic example of latrines, right? And you provide people with latrines, and you provide the community with the latrine, and they never use it. Or certainly not for latrine. They use it for a chicken coop, they use it to store grain, they use it for this, they use it for that, but they don't use it for the actual purpose of that a latrine serves. And it blows people's minds. I installed this latrine, you guys helped me, we did it all right, and why aren't you using it? And it's usually something subtle like, the latrine is the only place where there's a door that locks, and that's the only secure place, and it's more important for me to have a secure place than it is for me to have a hygienic place, and so therefore I'm not going to use the latrine for the intended purpose. So there's all these unintended consequences of any technology that you deliver, and you have to really think about those unintended consequences or unanticipated consequences if you're going to deliver something that's actually going to be used in the way that you are hoping it will be used. Does that help provide clarity to that subtlety? Yeah, so it's really hard to wrap your head around this because there's an infinite number of examples, but it's hard to make a really clean generalized statement because it's all subtle. One thing I thought was interesting about the energy outlook was the energy access index and how they rated everything, and whether that's actually the right way to approach things. like it's really useful to have energy and access index and to be able to compare where people are at, but are these different steps on each level actually the right steps? And that's open to debate, right? I'm not asking for a yes it is, no it's not. I don't know myself, but it is interesting. Like, do you actually prefer having a low voltage DC access that you control to a 240 volt connection that's poor quality and intermittent? I'd probably prefer step 3 than step 4. So I think that it's an interesting thing to read these documents critically, that even though this is like practical action and they're an amazing group and they're really thoughtful and love their work, this is still real hard stuff, and so it can be subtle. Were there any other thoughts people noticed? Yeah.
I wanted to see more comparisons, like when I was talking about the burn victims,
Mm-hmm.
like I wanted to know what that number was for the States, because it's something that I know. And
Yeah.
I was like, well, yes, 60% of people who came in with burns, it was because of cooking, or because of lighting. And I'm like, well, I feel like that's actually, like for us, a similar number would probably be cooking, because like how else do we really burn ourselves? So
Yeah.
it didn't have much to help me understand the numbers.
And some other subtleties are, how easy is it for you to get medical care, and what are the implications for you if you incapacitate your hand versus if you rely on your hands to feed your family every day. So there's other subtleties that are hard to see from just a 60% number, and even comparing to the US. But I will also try to post some resources that allow you to compare countries really easily, so that you can, if the documentation doesn't provide it, you can pretty easily look up on your own the comparison, if that's of interest. Okay, so we are fast approaching the end of the class. So this week, the primary homework assignment is what we call the Personal Energy Consumption Challenge. You may or may not know that in D-Lab development, students have to spend a week on $2 a day. And it's challenging, and it's really helpful. And so we were like, great, we're gonna make a similar energy assignment, but it's much more complicated to limit your energy than it is to limit your food spent, your financial spending, obviously, for some of the reasons we just talked about, that you can't just walk into a classroom and be like, I'm sorry, professor, you need to turn off that projector, and I need the lights off and the heat off, and I can't do my problem sets today because I can't use light and I can't use my computer because my other class said that, right? Like, we don't actually want you to fail for a given week, or make everyone in your world hate you because you're restricting, and it's much easier to control your personal spending than your personal energy. So the way we did this is we split it up into a few things. And the other thing is that most people have a budget or a general sense of how much you're spending on a given day or a given week, and very few of us, as we just figured out, have a sense of how much energy we're spending, consuming on a given day or week. So what I would like you to do is choose 2 days this week. And on the first day, actually spend your day documenting all the time, at all times, I'm using my laptop for this much time, I'm in a lit room for this much time, I'm in a heated room for this much time, I'm driving my car for this much time, all this stuff, and run through the numbers. So that you can get a more refined number than your initial estimate. I don't want you to spend 1,000 hours on this assignment, so it would be very easy to get so anal that you would have to spend a ridiculous number of hours on this assignment, and so you need to balance how refined your number is versus you have a life and you can't only spend it on my class as much as I think you should. So take that into account. One student last year I think spent like 80 hours on this assignment, and I really don't want that. And then some of the things you should think about is what is in your control and what is not in your control and what's sort of in your control. And then on the second day, and if it's possible, and I know there's within reason, if you can make the 2 days similar, so like if one day is a weekend and your weekends are totally different from your weekdays, if you can try not to do that, so that you can have a comparison that's vaguely legitimate. Try to implement cutbacks as much as possible to cut back significantly. Last year, one student cut back by taking shorter showers. That was the entire cut that they made, and that's insufficient. So try to really make it hurt, like it hurts to spend $2 a day for a week. But at the same time, try not to fail your classes. There's a balancing act there. And then document how hard was it to cut back, where could you cut back, what was out of your control, and then think about, but you don't actually have to experience, because it would be very challenging and prohibitive, is what if I said you have to use 10% of the energy that you're currently using? What would you do? If that was just a mandatory thing, how would you live? And then sort of run through that as a thought experiment, but you don't actually have to do it because it would be challenging. And the reason for the 10% is looking at the energy usage in the US versus in Nicaragua. And then the other assignments I just want to remind you of, one is if any plastic bottle, from like a personal water bottle or Coke bottle to a 2-liter bottle, we need for a lab coming up in a few weeks. So if you can look around your living group and collect a few and bring them in, that will make our lives a lot easier soon. And then the other thing is just a reminder that you should be practicing un poco español, por favor. So please do. Any questions on this homework?
Well, it's more on the plastic bottles. Is there a place for us to store the plastic bottles intermittently? For example, that way we don't have to bring in a whole bunch load of plastic bottles if we have them, and bring them in week by week.
Yeah, you can bring them in every week, and we'll collect them and find a place in here in the room next door to store them. So we need. We don't actually need that many, but it's nice to have an assortment, so when you're building your wind turbine, you can select the one that looks most appealing to you. So we don't need an infinite, so if everyone brought 1 or 2, that would be plenty. But some people, it may be easier than others to bring them in, so if, don't bring in 100, but if you can bring in 4, great. Yeah. Any other questions? Okay, so if you can fill out your muddy cards real quick, that would be great. Next lab is energy storage here, and next class is lighting and community partner intro.